Hello there. This is the section 11.1 video, the beginning of chapter 11, which is our last chapter for the course. It's our longest chapter for the course, and it's the most important chapter for the course. Specifically, near the end of chapter 11, we will learn about Taylor series, which has the most actual applications outside of a math class. But we're going to start off with 11.1, where we're going to introduce the idea of a sequence of numbers and talk about convergence and divergence, review L'Hopital's rule, and the squeeze rule. This is just a fundamental building block for series and ultimately Taylor series, the ultimate goal of the course. All right, so let's start with some definitions and some reminders. So right here, I have my first note. A sequence is defined to be an ordered list of numbers. So it's a list of numbers where you cannot change the order. It's already in an order and you cannot change that order. L'Hopital's rule is something from first semester calculus, where it says that if you're taking a limit of a fraction of two functions, it's actually equal to the limit of the derivative of the two functions, the fractions of the derivative of the two functions, but that's only true if our new limit of the derivative divided by the derivative exists, and either the original limit of the top and the bottom are both zero, or the original limit of the top and the bottom are both some version of infinity plus or minus infinity. So those are the requirements for L'Hopital's rule to be correct. Okay, so we're going to be using that as one method for helping us find limits. The squeeze rule for limits is if you have a limit and that limit is greater than or equal to a number. So let's say it's greater than n or greater than or equal to n, and it's also less than or equal to n. Well, then we know the limit has to equal n. In other words, suppose you had a limit and you could prove that it was greater than or equal to 7, and you could also prove that it was less than or equal to 7, well, then it's got to equal 7. There's no other possibilities. So that's a pretty basic idea that has the name, and we're going to be using that also to help us find some limits, although it seems like, why do we need it? But you'll see in a bit why it's helpful. And we finally have some vocabulary about converges and diverges. You've seen this before, especially with improper integrals, but I just wanted to define it here as well. A sequence converges if it has a limit equal to one single finite value. A sequence diverges if it's anything else, if it doesn't converge. So converging means it has a limit, it's equal to one number, and that one number has to be finite. All right, so I'll start with just some examples of sequences, and then we'll go from sort of there to determining convergence and divergence of sequences. All right, so I have some 5 examples here. So oftentimes we write a sequence with little curly brackets. So we have our first sequence here, looks like this. The n is just a counter. So for n equals 1, we would have 3 over 10 to the 1, which is 3/10. So n equals 1. My pen is not cooperating. Let's see if I can get it to work better. N equals 1. One more time. Is this first expression right here. And then 3 over 10 squared. If n equals 2, I get the 3 over 100. And if n equals 3, I get 3 over 10 cubed. So you get the idea that for each of these, you get a different value. For each value of n, you get a different value of the sequence. And it keeps going. And so that's a sequence. And it's just a pattern that we can recognize and write as 3 over 10 to the n. And you can imagine this keep going and going and going. So we end up with, down the line, 3 with 1 with a whole bunch of zeros, maybe 10 zeros if, n was something like 10. And this ends up being something where you get 3 over something infinitely large. And we would say this limit tends to 0. So this is an example of a sequence that ends up converging because the limit as n goes to infinity, limit as n goes to infinity, is 3 divided by an infinitely large number, which is 0. So it's a single finite number, therefore it converges. Okay, next up we have the sequence, which is just one half, one half, one half, one half. There's no counter n because it never changes. So n equals 1 is right here where we have a half. N equals 2 is right there where we have a half. N equals 3, we have a half. We always have a half. So this is just half, 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 half. And if you talked about the limit as n goes to infinity, I know there's no n, but we just use that to denote that we're trying to find the end of our sequence. Well, all the numbers are a half, so this is equal to a half, right? Since it's always a half, 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 its limit is going to be a half, and so we say this converges because one half is a finite number. All right, next we have 2 to the n. So when n equals 1, we have 2. When n equals 2, we have 2 squared or 4. N equals 3, we have 2 cubed or 8. So our sequence of numbers looks like 2, 4, 8, 16. And then we keep getting 32, 64. They essentially be multiplying by 2 every single time. So if we talk about the limit of this particular sequence, I guess I should put 2 to the n here. And maybe I'll just change this real quickly to say like the limit of our sequence 1/2 is equal to a half. So our limit of the sequence 2 to the n, well, this goes to 2, try to say color consistent. This goes to 2 to infinitely large number, right? And what happens to 2 to an infinitely large number? Well, if you remember your exponential functions, 2 to a super big number is infinity. Now, infinity is not a number, so it is not a finite number. So we would say this diverges. The limit of the sequence does not equal a finite value, so it diverges. All right, also run through the last couple. For the next one, we have 1/2, 1/3, 1/4. You can verify that those represent n equals 1, n equals 2, n equals 3. You could imagine it going to 1/10, 1/11, 1/12. Hopefully, many of you can see the pattern here that it's just increasing by 1 on the denominator each time. And this is going to, well, if I take the limit as n goes to infinity of this sequence, then it's going to 1 over an infinitely large number, right? So I can just say infinity or infinitely large number here. Some people just write 1 over infinity, which is basically the same thing. And that's going to be, well, what is 1 over an infinitely large number? 1 over 1,000, 1 over a million, 1 over a trillion, 1 over a Google, whatever. That's going to be closer and closer to 0. 1 over 1,000 is 0.001. 1 over a million is 0.000001. 1 over a Google is 0.0 with 99 zeros. And then 1. So it's like you have all of these numbers getting smaller and smaller and smaller. So it's equal to 0. So we call this converges because the limit is equal to a number. All right, lastly, my example is 3 plus -1 to the n. And I'll run through this one very carefully. If n equals 1, so n equals 1, this would be 3 plus -1 to the 1. And -1 to the 1, well, that's just -1. And 3 plus -1 is, in fact, 2. So that's the value when n equals 1. When n equals 2, over here, we have 3 plus -1 squared. And what is -1 squared? -1 times -1 is +1. 3 plus +1 is 4. So that's why the second number in this sequence is equal to 4. And the next number is going to be 2 again. And the reason why is if I put 3 into my formula, here's my formula. If I put 3 into my formula, I get 3 plus -1 cubed. And what is -1 cubed? Well, that's -1 times -1 times -1, which is -1. So this is 3 plus -1, which is why it's 2. In fact, anytime the exponent n is an odd number, you'll have -1 to an odd number, which will be -1, because you have an odd number of -1s being multiplied. And so that's why you get the 2 on all the odd numbers. 1, 3, 5 will always be 3 plus -1. And the other one, when you have an even exponent, -1 squared, -1 to the fourth, etc., you're going to get +1. So those will be 3 plus +1, which is why you get the fours each time. All right, so I just wanted to explain this sequence, which is 2, 4, 2, 4, 2, 4. So we need to find the limit of the sequence. So what does that equal? Well, pull an arrow there. So what does that equal? What does that tend toward? Well, it's either 2 or 4. You can't really say 3 because it's never 3. It's never getting closer to 3 or equal to 3. It's definitely either 2 or 4. Now, according to our definition, it converges if it's equal to a single finite number. This is sort of two different finite numbers. This is not what we call converging, so this diverges. So a lot of people think diverges as like infinity or something like that. I wanted to give an example where it diverges, but it's definitely not infinity. It's either 2 or 4, but because there's not consensus on what the limit is, we say it diverges. All right, so those are some examples of some sequences and some discussion about converging and diverging. Let's look at some more likely homework problems than just some introduction about sequences. So I have a half a dozen sequences here that we're going to discuss whether they converge or diverge. So how do we know whether something's converging or diverging? We just take the limit. So we're going to take the limit. Go back to my blue. Limit as n goes to infinity. What the book does is it doesn't even use the brackets. So you can use the brackets if you want and do ln n over n. But math people tend to leave the brackets off. So they're just doing the limit as n goes to infinity of ln n over n. And we're trying to see what this tends towards. Does this go to a number? Does it go to infinity? Does it hop between two different numbers? What does that do? And so you're going to have to go back to a little bit to your study of limits. Again, you did some of this when you were doing improper integrals. But let's look at this now. We have n going to infinity. If you remember from all your studies in algebra, the natural log function, as the input tends to infinity, the output also tends to infinity. It does it kind of in a slow way. It kind of looks like this. This is your graph of y equals ln x. Knowing what these graphs look like is very powerful. If you haven't memorized a bunch of them, there's about a dozen basic graphs, line, parabola. Like think about how many times knowing that an x squared looks like some U shape or upside down U shape, it's come in handy, right? Knowing that ln has this shape right here comes in very handy. So anyway, you can see that as n goes to infinity, the natural log ends up being something infinitely large. And as n goes to infinity, n also gets infinitely large. So this is infinity over infinity. And this is an exact candidate for using L'Hopital's rule. L'Hopital's rule only works when you have a fraction and the top and the bottom function independently either both go to 0 or both go to some version of infinity. And just go both to infinity. So we're going to say using L'Hopital's rule, and I'm going to communicate to my readers that I'm using L'Hopital's rule by doing something like that. I do the derivative of the top. I do the derivative of the bottom. I didn't leave enough space for my limit, so let me just do more space there. Derivative of the top, derivative of the bottom, and this new limit of the derivative of the top and the derivative of the bottom is equivalent to the original limit of ln n over n, as long as this limit actually exists. So as n goes to infinity, we have 1 over infinity on the top. And we have, I'm just going to use an arrow here instead of an equal sign, just for stylistic purposes. 1 is not affected by infinity or n or anything like that because it's just 1. It is a number. It is a constant, so I can write 1 there. What is 1 divided by an infinitely large number? Well, we had this discussion before. 1 divided by a million, 1 divided by a trillion, 1 divided by Google. This is going to be 0 over 1, and 0 divided by 1 is in fact 0. So this limit of the sequence equals 0. So what is our conclusion? The conclusion is limit equals 0. So this sequence, wait for it, converges. And that's the idea here of 11.1. Just get the idea of what a sequence is and determine if it converges or diverges. Here we use L'Hopital's rule to help us determine whether it converged. We'll see another example of that in the second one. If you remember L'Hopital's rule, or if I've reminded you enough about it, you can try number 2. Of course, you can pause and give it a go. I'm going to start this now, assuming that those who wanted to pause have done so already. So I can take the limit of this fellow. And you might imagine that this is infinity on the top and infinity on the bottom. Infinity times infinity is infinity. E to the infinity, like 2 to the infinity, is infinity. So I'm going to use L'Hopital's rule. L'Hopital's rule just simplifies the limit. It doesn't find a limit. It just simplifies the limit. So I still have to write limit because I have not found the limit yet. I'm just simplifying it using derivatives. The derivative of the top, derivative of the bottom, like that. And what happens at the top now? Well, 2 times n is 2 times infinity. And e to the n, we already know is infinity. So it looks like it may not have worked because you still have infinity over infinity. We have this new limit, which is equivalent to our original limit, but it's still infinity over infinity. So what do we do now? Well, we evaluate this new limit any way we want. And one way we can evaluate it is using L'Hopital's rule. Again, yes, there's no restriction. No one said you can only use L'Hopital rule once in your life. You can use it as much as you like. This new limit is still infinity over infinity. So we're still allowed to use any method we choose to simplify it. I'm going to use L'Hopital's rule once again. That gives me the limit as n goes to infinity. The derivative of 2n is 2. The derivative of e to the n is e to the n. Now we have 2 over infinity. 2 over infinity goes to 0. So we have the limit of this thing. Equaling 0. Thus, we know that this limit converges. It's equal to a number. All right, next one. I'll do that in green. All right, so we're doing our limit thing as usual. These are all limit problems. We have 5 times infinity to the 6th, which is going to be like really big infinity, minus 7. Infinity minus 7 is still infinity. On the bottom, we have 9 minus 10 times infinity to the 6th. So this is infinity minus 7, which is infinity, and 9 minus infinity, which is negative infinity. But even though these aren't the same version of infinity, L'Hopital's rule can still be used. It can be used when top and bottom are both 0, or top and bottom are some version of infinity. It doesn't matter that they're the same plus plus or minus minus infinity. So once again, I'll use L'Hopital's rule. Derivative of 5x to the 6th. Derivative of this top function is 30x to the 5th minus 0. Derivative of minus 7 is minus 0. On the bottom, I have 0 minus 10 times 6 is 60, x to the 5th. Well, look at that. So even though the top and the bottom are still like infinitely large, oops, I forgot my little limit thing. So I'm going to move this over a little bit. If you haven't taken the limit, you are obligated to continue writing LIM. Like until you take the square root of something, you have to keep writing that funny square sign. So until you actually find the limit of something, you must continue writing the limit symbol or word or whatever. So in this particular situation, I made a mistake. Anyone may see my mistake? 5 times x to the 6th. People are saying, how'd you get 60, Jim? And the answer is, I don't know math. if I differentiate 5x to the sixth, I don't get 60x to the fifth. I get 30x to the fifth because 6 times 5 is 30. Nonetheless, I do have something infinitely big on the top, infinitely big on the bottom. I could continue to use L'Hopital's rule, but a smarter thing would just be to simplify this. We can simplify it using L'Hopital's rule, or we can simplify using lots of other techniques, like division. Okay. So in this case, I have x to the fifth divided by x to the fifth is just 1, and 30 divided by negative 60 is negative 1/2. So what is the limit as n goes to infinity of negative 1/2? We have negative 1/2. The n does not affect the 1 or the 2 or the negative. There's no n in this formula. It's just constants. So I don't care what n is 5, n is 50, n is a million. This value right here is still going to be negative 1/2. It is unaffected by n. So what does this tend to be? Well, negative 1/2. In my introduction, I gave you an example where we had 1/2, 1/2, 1/2, 1/2, and the limit was 1/2. Here we have negative 1/2, negative 1, negative 1/2, negative 1/2, and the limit is equal to negative 1/2. So once again, we know that this sequence, this sequence right here, 5x to the sixth minus 7 over 9 minus 10x to the sixth, this converges because it's equal to a number, negative 1/2. All right, we got, I think, 3 more examples. Yeah, 3 more examples for this video. All right, so next up, we have this sequence right here. So, of course, I'll be taking the limit to see what happens in terms of converging and diverging. All right, so we get e to some negative infinity on the top, and we have infinity on the bottom. So we can use L'Hopital's rule, right? We have some infinity thing, so we can use L'Hopital's rule. Well, that was kind of like a trick. I tried to set people up a little bit there. You have to actually evaluate this. This is going to be e to the negative infinity over infinity squared. And I definitely know that the bottom is infinity, but what is e to the negative infinity? Once again, if you remember your basic graphs, any exponential function looks like this. And this is y equals e to the x. If you have a negative infinity, we're going way over here. E to the negative infinity is 0, not infinity, not negative infinity. E to the negative infinity is 0. You're basically saying 1 divided by e to the infinity. 1 divided by infinity, once again, is 0. So no L'Hopital's rule. It does not apply in this situation because we don't have one of the indeterminate forms, 0 over 0, or infinity over infinity. So what do we do? Well, we can simplify this using algebra. We know that I'm running out of room, but I'll figure it out. This limit of e to the negative n over n squared, I can use my algebra to write this as 1 over e to the n squared, because negative exponents are reciprocals. Once again, I forgot my limit, so I have to squeeze things in. There we go. So this one ends up being 1 divided by something. E to the n is infinity. N squared is infinity. 1 divided by infinity times infinity is 1 divided by a very, very large number, like infinity, which tends to 0. So we know that this thing converges. I have to write my conclusion on the right side since I'm out of space. If I can move this over, let me try this. Oh, maybe I don't have room to move it over. Let me try this. There we go. All right, so my conclusion is that this sequence converges because it's equal to a number. So the sequence converges. Okay, a couple more examples here. Let me go back a little bit so you can see it. Okay, so my next example, 6 root n over 6 plus root n. Let's see. On the top, the square root of infinity is still infinity. So we have 6 times infinity on the top, and we have 6 plus infinity on the bottom, or 6 plus the square root of infinity, which is 6 plus infinity on the bottom. So we have infinity over infinity. So once again, we can L'Hopital's rule. It's a very, very handy rule. If it's not indeterminate, if it's not infinity over infinity, if it's not 0 over 0, we can usually figure it out without having to do anything more complicated than just some basic algebra. If it is 0 over 0 or infinity over infinity, L'Hopital's rule is fantastic in being able to simplify this. So I'll start by writing my limit so I don't forget this time. The derivative of 6 times root n is 6 times 1/2 n to the negative 1/2. The derivative of 6 plus square root of n, the 6 goes away. I said 1/2, but I wrote 1 over n. Right, the thing I said. I said 1/2 n to the minus 1/2. There we go. The bottom has a derivative of 0 plus 1/2 n to the minus 1/2. We can simplify this using algebra, dividing the top and the bottom by the exact same thing, leaves 6, because the 1/2 divided by 1/2 is 1, and n to the negative 1/2 time divided by n to the negative 1/2 is 1. And so this limit is equal to 6. So once again, we have a converging sequence. All right, 2 more examples, and I'm going to show you a little bit. Okay, 3 more examples, and I'm going to show you a little bit about the squeeze rule. Okay, for this one over here, oops, where's my blue? This one over here, we have the limit as n goes to infinity of -1 to the n over n. The top part kind of goes between -1 or +1. I talked about this example when n is an odd number, -1 to an odd number is always -1. If n is an even number, then -1 to the n is always +1. So we go between -1 and +1. The bottom part is n, which is tending to infinity. But we got to be careful with infinity, because just because there's infinity in one place doesn't mean we're guaranteed of anything. There are definitely ways to argue this about what you think the limit's going to be, but I'm going to show you the squeeze rule and how it can be used here to definitively say what the limit is going to be. So you may have an idea, maybe your intuition is correct, but I'm going to show you the squeeze rule. So you know that this is either -1 or 1. So I can say for sure, so we know that whatever our limit is, it has to be at least as big as -1 over n. Oops, again, forgot to leave room for my limit sign. So, so we know that it has to be at least as big as -1, because it toggles back and forth between -1 and +1. We also know that it has to be at most +1 over n. Where's my limit, Jim? Limit of +1 over n. So we know, because the top is going between -1 and +1, that the limit of this -1 to the n thing, it has to be at least as big as -1 over n. It can't be smaller than that, because it never gets smaller than -1 on the top. And it also, in a similar argument, can't be larger than 1 on the top. So it's between this sort of -1 over n limit and +1 over n limit. But the limit, as n goes to infinity, of -1 over n is -1 over infinity, which is equal to -0 or 0. And similarly, the limit as n goes to infinity of 1 over n is 1 over infinity, which is 0. So we know for sure that our limit is greater than or equal to 0 but it's also less than or equal to 0. So therefore, we know that it's equal to 0, right? It can't be greater than or equal to 0 and also less than or equal to 0 unless it's in fact equal to 0. So our limit of this creature here is equal to 0. And so our sequence of numbers given by this pattern converges because the limit is equal to a number, a finite number. I guess most numbers are finite. So there we go. There's our argument for that example there. All right. The next one is also going to be done using the squeeze rule. If you want to try that, it's a good time to pause and give that a go. Remember, it's always nice to watch videos, but until you start doing the problems yourself, you're not really sure if you didn't remember all the steps or all the little twists and turns that come when we change the problems around. So it's nice to practice a little bit to get your sort of experience and your confidence both up. All right, so for those who have paused, I'm sure you're back since you're watching this video, and I will do this thing right here. All right, so sine n is lots of different numbers. It's not -1 or 1. Sine of 1, if you want to look at like a calculator or something, sine of 1 is 0.841. Sine of 2 is -0.909. Sines have different values, right? So you can find different sine values. They don't seem to equal a pattern that's noticeable, at least. Positive 0.8, negative 0.9, negative 0.1, etc. So what do we do with the sine n over e to the n? First of all, let's see what happens when we plug in infinity. We get sine of some infinitely large number divided by e to the infinity. E to the infinity is definitely infinity, so there's definitely an infinity on the bottom. The question is there also like infinity on the top where we can use like a L'Hopital's rule? Well, so far when I looked at the values of sine 1, sine 2, sine 3, none of them looked like they were tremendously large. Once again, if you remember your like 12 basic function graphs, you might remember that sine, let me do it in red over here, sine has a graph that starts at the origin or starts at the midline and goes up and down and up and down and up and down. And this also goes backwards up and down. It has a height of 1 and a depth of -1. And this corresponds to a unit circle where sine measures the y value. The y value in a unit circle has a maximum of 1 and has a minimum of -1. So it just toggles between 1 and -1 as we rotate around the circle. Y is 1, y is 0, y is -1, y is 0, y is 1. Goes around and around and around. Sine is just measuring the y value, so it goes between -1 and 1. So we actually have a very similar argument for this problem right here. We know that the limit we're looking for, this sine n thing over e to the n, it has to be no smaller than -1 because sine never gets smaller than -1. And it has to be also less than or equal to +1 over e to the 1 because once again, sine never gets higher than 1 and sine never gets lower than -1. And we can argue that -1 over e to the infinity is -0, which is the same as +0, so it's 0. Our limit right here. And with the same kind of logic or justification, 1 over e to the infinity, 1 over infinity is 0. So we know that the limit as n approaches infinity of sine n over e to the n is both greater than or equal to 0 and less than or equal to 0. So no, it's equal to 0. So now we know the limit, and we also know that this thing converges. All right, I am doing a bad job with my board management, but what else is new? So this limit is equal to 0. And so we know that the sequence it's better converges. Sorry for being slow. All right. We got a last example. This is not a squeeze example on the last example. I thought I'd throw in a harder example to show you the kind of analysis that goes into harder problems. So this problem is over here. I'm going to have to write it down below because I'm running out of space. So I'll write it over here. It's the sequence of 2 to the n over n plus 1 factorial. So we're looking for the limit as n goes to infinity of 2 to the n over n plus 1 factorial. And as n goes to infinity, the top goes to infinity. As n goes to infinity, infinity plus 1 factorial is also infinity. So I have infinity over infinity, so we can use L'Hopital's rule. The problem with L'Hopital's rule is that it requires us to differentiate the top function and the bottom function. The derivative of 2 to the n, we know what that is. Derivative of 2 to the n is 2 to the n ln 2. The derivative n plus 1 factorial, we do not know. There's no formula on your formula sheet about the derivative of a factorial. So I gave an example where it's not as simple as just using L'Hopital's rule. So here's the analysis here's an example of the analysis for this kind of problem right here. So to help explain this, I'm going to write out some terms. So for n equals 1, that would be 2 to the 1 over 1 plus 1 factorial, which would be 2 factorial. For n equals 2, we get 2 squared over 2 plus 1 factorial, 3 factorial. I'll write a couple more. For n equals 3, I get 2 to the 3. 3 plus 1 factorial is called 4 factorial. And I'll write out one more here. It'll be 2 to the 4th over 5 factorial. Okay. So now I'm going to write them out a little bit, long ways so we can start seeing some of the patterns. This is 2 over 2 factorial. If you remember factorials, it's just the number counting down to 1 multiplied all together. So 2, 1 multiplied by each other is 2 factorial. The top is 2 squared. I'm going to write this as 2 times 2. I know maybe you want to think of it as 4, but it is 4. I'm going to write it as 2 times 2 so we can start seeing some patterns. 3 factorial, I do 3 all the way down to 1, multiplying everything together. So 3 factorial is 3 times 2 times 1. Next, we have, I'll put commas here, I guess. Next, we have 2 cubed, which is 2 times 2 times 2. And here we have 4 times 3 times 2 times 1. And I'll do one more. All right, so that's what these things look like. All right, so you may notice that they all have like a 2 in the top and a 2 in the bottom that you can imagine like, canceling out or dividing to equal 1. And now all of them have basically, well, except for the first one, which is just 1, but let's think of the next one. You have 2 over 3, right? And the next one you have is 2 times 2 over 4 times 3, which I can write as 2 over 4 times 2 over 3, right? You don't have to write them as separate fractions, but you remember, think of the fact that you're multiplying and dividing. So it's 2 times 2 over 4 times 3, or 2 over 4 times 2 over 3. And this one would be 2, 5, and then 2 over 4 and 2 over 3. All right. This is let me make it just clearer so people don't get confused later on. All right, and I'm just going to remind you of one more little bitty thing that I'm sure you guys remember, but I'll just remind you anyway, just in case. If I have a fraction, let's suppose I had 2 over 3, and I have another fraction with the same numerator and a larger denominator. So 2 over 3 versus 2 over 5. Which is a larger number? If you had 2/3 of something is that bigger or smaller than 2/5 of something? A lot of you are saying, well, geez, we know what that is. 2/3 is larger and 2/5 is smaller. 2/5 is smaller than a half, by the way, and 2/3 is larger than a half. So making the denominator larger, the denominator larger results in a smaller value. Right? And similarly, you could say that making the denominator smaller results in a larger number. So I'm going to put that over here. So making the denominator smaller. So if I went from 5 down to 3, results in a larger number, larger value or number. Okay, so that's something that I think makes sense for people to think about. But it's something that you're in the middle of doing 6 different things. Sometimes it's not as obvious. So I just wanted to make sure that we had that on our mind. So I have these fractions. The first fraction is 1. Then we have 2 over 3. And then I have 2 over 4 and 2 over 3. I have 2 times 2 over 4 times 3. What if I make this 2, 2, 3, 3? What if I make the denominator smaller? What happens to the value of this thing? If I make the denominator smaller, it results in a larger value. So this thing right here is larger than this one over here. I made the denominator smaller, so the result is larger. I'm going to do the same thing over here, making them all 3s. So 2, 2, 2, 3, 3, 3. Each time I made the denominator smaller. So maybe I should say like a box. This whole thing is larger, right? This whole thing is larger than the one over there. So when I make the bottom numbers smaller, 5 went to 3, 4 went to 3, 3 stayed 3, but the whole thing is, the whole denominator is smaller. Once again, if the denominator is smaller, then this whole thing is larger than the one above. Larger than this one here. Why am I doing this? What's the method to my madness here? Well, this thing that I have, so the larger sequence would be 1. That's from this guy. 2/3. 2 times 2 over 3 times 3. 2 times 2 times 2 over 3 times 3 times 3. And can you see the pattern now? The next one, although I haven't written it out, is going to be 2 times 2 times 2 times 2 over 3 times 3 times 3 times 3. The larger sequence is just 2 to the n over 3 to the n. So by reducing the size of the denominator to 3, 3, 3, 3, 3, each of these fractions became larger and larger and larger. So I know that 2 to the n over 3 to the n is a larger sequence than we started with. So what am I doing here? Well, my original sequence was 2 to the n over n plus 1 factorial. And I know that this new guy is larger. So larger, 2 to the n over 3 to the n. I shouldn't do it with brackets. I should do it with limits, but I'll do it in brackets just because I talked about each individual term. So each individual term of these 2 to the n over n plus 1 factorials, right? All those terms are going to be less than or equal to 2 to the n over 3 to the n. Okay, and then I also know that the sequence of 2 to the n over n plus 1 factorial, 2 to the n over n plus 1 factorial, that's the, I guess we can even start up here. That's the 2 on the top, 2 times 1 on the bottom, 2 times 2 on the top, 3 times 2 times 1 on the bottom. Before we did any simplifications, we had all these 2's on the tops. We had all these numbers, 5, 4, 3, 2, 1 on the bottom. No matter what those are all positive numbers. So I could say that it's larger than 0. So I have my sequence where I know that all the terms of the sequence are less than 2 to the n over 3 to the n, but I also know that they're all positive. So now I write it in the specific squeeze rule formula or format. The limit as n goes to infinity of 2 to the n over n plus 1 factorial must be less than or equal to the limit as n goes to infinity of 2 to the n over 3 to the n, which has to be greater than or equal to the limit as n goes to infinity of 0. Well, we know the limit of 0 is 0. And what about 2 to the n over 3 to the n? I can use algebra to help me simplify that. That is 2/3 to the n. 2/3 is a fraction. So for fractional exponential functions, a fractional exponential function looks like this. This is y equals, I will call it b to the x if b is a fraction, so less than 1, right? So it goes down. It's a decreasing function because you're multiplying by a number less than 1. It's getting 2/3 smaller, 2/3 smaller, 2/3 smaller, 2/3 smaller until it gets infinitesimally close to 0. So we have our limit is greater than or equal to 0. It's also less than or equal to 0. So yes, what we now know is our limit is equal to 0. And therefore, our sequence converges because it has a limit, which is a finite value. So I'll just write that down here at the bottom. So the limit of our formula, our sequence, is equal to 0. That's by the squeeze rule. I'll say by squeeze rule. What do we know? We know that our limit is equal to 0. Thus, we know that the sequence, wait for it, converges. All right, so there's some examples of problems in which you are asked whether the sequence converges or diverges. I'm trying to get it on one page, but it's going to be very small. I'm not sure if that helps people in terms of like seeing the whole thing. But there you go. There it's on one page with teeny tiny font. I'll zoom into the top and I'll zoom into the bottom separately in case people have taken screenshots or things like that. But that is the end of today's video. That is how we find, oh, I didn't make it all the way up. So there we go. There's all the problems on one page. So this is how we sort of analyze sequences in terms of whether they converge or diverge. So I hope that this video was helpful to you, and that if you have any questions, that you'll let me know. Perhaps I'll see you in my Zoom hours. Perhaps you'll just email me and let me know if you have a question or maybe a different kind of problem that you're curious about, and I can certainly give you my advice on that one. All right, so I hope you have an enjoyable day, and maybe I'll see you in the next video.